Hey, PCamsters, this is Mrs. Vanderlei bringing you Chapter 9, Blank Walls. We have already done part of this unit back when we did Lewis dot structures and things like that. So we're going to go and finish off this chapter now, okay? So we're not going to just do covalent bonding, which is what we did earlier before Christmas. We're going to talk about some ionic bonding, and then we have one more delta H. Your good old enthalpy comes back one more time. And you know what? And then that will be it for really the year. So it's kind of exciting stuff, isn't it? Alrighty, Rose. So let's see where we begin. So chapter 9 is like types of chemical bonds. And well, first of all, before we talk about types, well, what is a chemical bond? Bonds are attractive forces that hold groups of atoms together. So we have different types of chemical bonds. We have covalent, which we already talked about, which would be non-metal, which are sharing their electrons. And again, this beginning part is going to be more about the ionic bonds, which are your metals and nonmetals, okay? So why do chemical bonds form? Well, they form because they will lower the potential energy between the charges of the atom, all right? And so here's my picture. What's going on? If I have two atoms coming together, at some areas they're going to be too close together. And so if they're too close together, that means their nuclei are going to be too close together and they're going to repel each other. So those positive protons in the nucleus are too close, they're going to repel. If they're too far apart, then there is no attraction whatsoever. So just like, Goldilocks and Three Bears or their porridge, this is too close, this is too far, and the chemical bond is just right, okay? So that means there is enough traction between the outer electrons of one atom and the nucleus of the other one, and vice versa, the outer electrons of the other one to the nucleus of the other one. Also, they're not so close that the nuclei are not repelling each other. So that would be your optimal distance for your chemical bond, okay? So it says, I kind of alluded to this too, when two atoms approach each other, three things can happen. The electron repulsion can happen. Proton repulsion, that means if the nuclei gets too close together, and then the proton-electron attraction, and that's what really causes the bonds, all right? So again, I've sort of alluded to this. Ionic will be the electrons are transferred, one's given to the other. Metal, nonmetal. Metal, nonmetal, I think I said that. Non-metal, nonmetal is your covalent, where electrons are shared. And we've also alluded to the metal and metal, which is a metallic bond. And we talked about the sea of electrons. Remember when I had a group of you come up and holding those negative parts? That's it, sea of electrons. Okay, so it'll be your metal. Let's go to the next page. All right, so really we're going to talk for the most of this rest of this video about ionic bonds. And it's called the electrostatic attraction between ions. Now, what the heck does that mean? Electro means, well, what do you think it means? It means there's those charges. Static means they're not moving, all right? So the atoms are pretty much stuck in a fixed position. Attraction between ions. They're produced by the reaction between a metal cation and a non-metal anion. Hopefully those terms are still familiar. And number 2 is a biggie, all right? So here, let's star this. All right, I think it deserves 4 stars, okay? So Coulomb's law is a very important concept. It's used in a lot of applications. And so we are going to use Coulomb's law to calculate the energy of an ionic bond. And so here's the equation. Again, if you need it, they'll give it to you. But I think the concepts, they may not give you the formula, but you should know the concepts, and we're going to go over those. So here's the formula. E equals 2.31 times 10 to the negative 19th joules times what? Nanometer. This is one of the few occasions where you don't have to know the meter, you have to know the nanometer. Okay, so write that as a note. You stay in nanometers, or if necessary, you convert it to nanometers, okay? And then you have Q1, Q2 over R. Well, what is all this stuff? Well, R is the distance between the ion centers in nanometers, all right? So the distance between one nucleus and another nucleus, that's your center. That's your R. So J is the energy in joules, obviously. And what's this Q1, Q2? Q1, Q2 is the charges, all right? So this is your +1, +2, -1, -2, -3. So it is the numerical ion charges. And then what it said, don't neglect their signs, okay? Why would that be true? Because think about it. If you have E equals 2.31 times a negative number, then energy is negative. So when these ions come together, energy is released. So it's kind of like this. Two magnets are coming together. Whoop! All right, did you hear that? I clapped. All right, so what does that clap mean? It's when those two positive and negative charges, boom, come together, energy is released. So it's a negative sign, okay? And so I even wrote that there will be negative sign on the energy once calculated. Why? It indicates an attractive force so that the ion pair has lower energy than the separate ions. Energy is then released. Okay, so let's see what this problem is. All right, so it says in a solid sodium chloride, the distance between the centers of a sodium ion and chloride ions is 0.276 nanometers. Calculate the ionic energy per pair of ions. All right, so here is our equation. And so E equals 2.31 times 10 to the negative 19th joules nanometers, Q1, Q2. So what's the first thing? Well, what's Q1, Q2? What's the charge of sodium? +1. What's the charge of chloride? -1. What's R? 0.276 nanometers. All right, so notice I put the charges here and I put nanometers on the bottom. Hey, what's going to happen to my nanometers? I believe they're going to do what? They're going to cancel each other out. Do you see that? So they cancel each other out. And so what's my only unit left is joules. So now it's the only thing left is to actually calculate this stuff. So here I have, oh, I should have canceled them out here too. Here, I'll cancel them out again. So nanometers cancel out again. Here we go, here we go. And so now it's 2.31 times 10 to the negative 19 joules times negative 3.62, 1 over nanometers. And I end up with a negative 8.37. It needs to be negative, all right? It needs to be negative. Energy is released. We also said energy is going to be lowered, so it becomes negative, more negative, when you have the optimal distance between the two. So what does this mean, all right? Why don't you go ahead and in this space right here, write this down. This is important, all right? And this, I should probably put some stars around here again, okay? And this is the concept that they probably won't give you an equation for it. You have to understand the concept of Coulomb's law, all right? So what kind of things do you notice here? What is energy directly related to? Energy is directly related, is directly related to the charges. All right, so as the charges increase, energy increases. What does this mean? What if I had magnesium chloride? We have a +2 and a -1. Then this would be a +2 and a -1. So it'd be a 2 on top, wouldn't it? So if my numerator here goes up, then my energy goes up. All right, so it says greater the charge, the greater the attraction. Hopefully that makes sense to you. All right, what else does this mean? Well, what else is energy related to? It is related indirectly to distance. So what would happen if the 0.276 was a bigger number? All right, so what does that mean? The greater the distance, what would happen to E? All right, the less attraction. Or in other words, how about the smaller the distance, the greater the attraction, all right? So that would be, an indirect relationship. This is what you need to know. And we're going to come back and see this again. And finally, there are some consequences. All right, so you could actually predict the boiling points of ionic substances, all right? So if the attraction goes up, it's going to be harder to separate them. If the attraction is lower for whatever reason, then it's going to be easier to separate them, okay? It's still going to be a pretty big number. We're talking about in the hundreds. Remember, like melting, what did we try to melt? I forgot already, in that one mini lab, all right? It was really hot. Oh, that's right, it was the copper thing. Wrong idea, but it's going to be really, really hot. We're going to be in the hundreds, maybe the thousands of degrees Celsius to melt ionic substances. However, we can still rank them, which ones have a higher boiling point, which ones have a lower boiling point. Okay, so that would be a consequence. So hopefully you wrote all this down, that you maybe had to pause it because maybe you have me on double speed or something, all right? But make sure you have that written down and make sure you understand these consequences, okay? All right, let's go on to 9.3, okay? All right, representing valence electrons with dots. Okay, I'm probably going to go through this really, really quickly And so, because I think you have a good grasp on this, but I just want to make sure I just don't gloss over anything. So what's a valence electron? It's the outermost electron. So if I'm looking at my energy shells, I have a 1, 2, 2. Hey, what's my biggest number, 1, 2, or 2? It's 2. So how many electrons total do I have, valence electrons it is for action? I have 6. So I'm going to go 1, 2, 3, 4, 5, and 6. Does that ring a bell? I sure hope so. So draw the Lewis diagram for each element below. I'm just going to kind of go across here because whatever is true in this column will be true for this column and yada, yada, yada. So lithium has 1, beryllium has 2, boron has 3. I think you get the idea. Carbon has 4. All right. Nitrogen has 5. Oxygen has 6. Fluorine has 7. And neon has, I'm just going to do it this way, 8. Hopefully you knew that. So whatever you did in the second period is true for the third period. Hydrogen has 1, but what's special about helium, all right? Does helium have 8? Nope, helium has only 2. Why only has 2 electrons? It has the 1s2. Now notice the difference between helium, all right, and beryllium. I paired up those valence electrons because they're the 1s2. They are paired up. Here I did not pair them up. I know it's a 2s2, but there is a 2p orbital available to promote and separate those 2 electrons, okay? There is no 1p orbital to separate these into. All right, so that's what's special about helium. Hopefully that looked familiar. Let's go on. So if the electrons are transferred, if you have a metal-nonmetal, an ionic bond is formed. Metals will what? Give to the nonmetal. So the nonmetal has a filled 8 electrons. If electrons are shared, all right, each nonmetal will have 8 electrons around it. And again, what's an octet? 8 electrons. And I'm going to stop right here. 9.4 is a very long, and it'll probably take me more than 15 minutes to get through 9.4, but it's also very important, okay? So I'm going to stop here, and again, don't wait to be great. Bye-bye.